Hello, everyone. It is my great pleasure to introduce today's champ speaker, Tim Tribone from Syracuse University, who will tell us about branched covers and matrix factorizations. Tim.
Thank you very much. Thank you, Lisa and Carrie, for the invitation to talk today. I'm very excited to tell you guys a little bit about branch covers and matrix factorizations. And yeah, so let's get right into it. So I am doing a slightly different style of presentation, and hopefully it works out really well. But if there's any hiccups, I apologize in advance. So let's try this. Okay, that works so far. So we are going to talk about those two objects, which I just swiped from, branch covers and matrix factorizations. And I want to tell you about what they are and then how they're connected. And hopefully you can leave having a solid idea of why these two ideas should be related. So first I'm going to say a little bit about some background about matrix factorizations, and then I'll get into the newer stuff. So I'm going to start with a regular local ring. And if at any point I write something that you can't read, please just let me know. And we're going to fix an element f in this ring. We usually take it to be non-zero and non-invertible. And so a matrix factorization of this element f is a pair of matrices. I'm going to call them phi psi. They're square with entries in S. And the main point is that their product, if you take them in either order, gives you F times an identity matrix. So phi times psi is a diagonal matrix with F's right down the diagonal, and same with psi times phi. So if this is a definition you haven't seen before, let me just give you a quick example to keep in the back of your mind. So let's look at a polynomial x cubed plus y to the fourth in this power series ring in two variables. So so you might notice that this is an irreducible polynomial, but let's go ahead and factor it anyway. But we're going to use matrices to do this. So I can do something like this. And I'll multiply these just to show you. So I've cleverly laid out some input values here. This obviously, well, maybe not obviously, but this isn't going to work. But if I put in some minus signs in some clever places, it will work. And you get a nice factorization of this guy in terms of matrices. So what I mean is when you do the product, you get x cubed plus y to the fourth down the diagonal and zeros everywhere else. So this is a 2 by 2 matrix factorization of x cubed plus y to the fourth. Okay, great. So besides being pretty satisfying to do this sort of thing, you can play around with the exponents and see what other ones you could make. Besides being satisfying in that sense, why do we really care about these objects? What's their connection to modules over the hypersurface ring defined by our element F? So let's go ahead and set R to be this hypersurface S by the ideal generated by F. And I want to go ahead and make two observations. So the first is that since this product, phi times psi, and also the other way, psi times phi, since these are F times an identity matrix, and F is a non-zero divisor in our regular ring, what we get is that both phi and psi are injective. So actually, we get a nice short exact sequence, which looks like the following. For some n, and I'll just stick with phi for now. So that's good. And then secondly, the other thing that I just want to point out is that if you consider multiplication by f, well, that's the same thing as multiplication or the composition phi psi. and the multiplication phi psi. And so that's contained inside the image of phi, because phi sits on the outside here. And so the point is here that f is going to kill the co-kernel of phi, which in other words means the co-kernel of phi is naturally an R module, where R again is our hypersurface up above. So from each matrix factorization, we're getting an R module, and in fact, it's an R module which has projective dimension 1 over the base ring S. Okay, and it's not just any old R module, it's a special type of R module, which I'm going to tell you about on the next page here. Okay, so I've pre-written these definitions, but let's just talk through them quickly. So the special type of R module that it is called a maximal Cohen-Macaulay module. If you have a finally generated module over a local ring A, call that maximal Cohen-Macaulay if the depth is equal to the dimension of the ring A. In other words, the maximal possible value. And then the Auslander-Buchsbaum formula tells us if we have a module of finite projective dimension, then you can compute the depth nicely in this way. And when we combine all this stuff together on the next page, but the point is that if you have a matrix factorization of F, call it phi psi, then we can compute that the depth of the R module associated to this matrix factorization is equal to the dimension of the ring S minus the projective dimension of the module. So I'm computing the depth over the ring S, but the depth doesn't care if you compute over this regular ring or the quotient. And then the dimension here is the same because S is also Cohen-Macaulay, but I'll just avoid that point for now. And so we already saw that this guy had value 1, the projected dimension was 1. And so the depth of the co-kernel phi is precisely 1 less than the dimension of S, which is the dimension of R, and therefore co-kernel of phi is MCM over R. So this is the point. So given a matrix factorization, the co-kernel of either map, in fact, is a maximal Cohen-Macaulay module over the hypersurface ring. And what's nice about this is it goes the other way as well. So if you start with an MCM module over the hypersurface, I'll call it M. Well, because it's MCM over R, that means it's going to have projected dimension 1 over the regular ring, reversing these arguments above. And it turns out that this will mean we'll have a short free resolution over S like this. And then if you go and you compute multiplication by F on this complex, put some F's in here. Well, M starts life as an R module, so multiplication by F on M is 0. And therefore this chain map is, this is a phi down here as well, is null homotopic. So we get a back map like so, call that psi, and we get that this little triangle commutes, meaning that phi times psi is F times the identity on this Sn. So we recover a matrix factorization from this MCM R module. So phi psi is a matrix factorization. You can check that the other composition will also be, I guess it's this other part of this triangle here. And then the co-kernel of this phi will be M again as well. So from a matrix factorization, we get an MCM R module, and from an MCM R module, we get a matrix factorization. Okay, and then this is really the content of a theorem of Eisenbud's, which is sort of the foundation for which the theory of matrix factorization sits upon. So let me just write this out quickly. So the functor, which we just described in part from, I'm going to write the category of matrix factorizations like this, MF of F. So the functor, which we just laid out, which takes a matrix factorization and it sends it to one of the co-kernels. You could pick either one, but it usually pick the first one here. This induces a bijection between what are called reduced matrix factorizations of F and MCM R modules with no free summons. Okay, and this word reduced, I'll just sneak in down here. This just means that the entries of phi and psi live in the maximal ideal of S. Okay, and so this, what Eisenbud's theorem really says is that we should think of matrix factorizations and MCMR modules as sort of one and the same thing. We should identify them. Matrix factorization gives you a really concrete way to think about an MCM module over this hypersurface ring R. Okay. Excellent. Okay, so now I want to tell you about a little bit more about the motivation for the results that I want to talk about later, which is about the representation theory of these hypersurface rings. So let me just recall that a local ring A is said to have finite Cohen-Macaulay type. So I wrote CM here for Cohen-Macaulay. If up to isomorphism, there's only finitely many of these MCMA modules, specifically finitely many indecomposable ones. So in the representation theory of these hypersurface rings, we're on a search for hypersurface rings which have only finitely many indecomposable MCM modules. Okay. So that's for a general local ring, but as I was saying, for a hypersurface, based on Eisenbud's theorem, this is equivalent to saying that there are only finitely many indecomposable matrix factorizations of this element now. Saying that there matrix factorizations, and I mean indecomposable, of F. So let me just reiterate that really quickly. So if you have a hypersurface ring with finite Cohen-Macaulay type, that's equivalent to saying that there are only finitely many indecomposable matrix factorizations up to isomorphism, because these two categories are actually equivalent. Excellent. Okay, so let me just give you which I'm calling R, which is going to be again power series ring in two variables modded out by x squared. And what I claim is that this hypersurface ring is not of finite Cohen-Macaulay type. And how can we see that? Well, we can write down quite easily an infinite family of indecomposable matrix factorizations of x squared over the space ring. Okay, so this is a construction due to book fights Royal and Schreier in 1987. And so here's a list of infinitely many matrix factorizations of this polynomial. So we're going to do something like this. That's an n. Again, we have to, this won't work, but if I put in some minus signs, then it will. So here is this pair of matrices is a matrix factorization, an indecomposable matrix factorization of x squared for all n bigger than or equal to 1. So we get a family of indecomposable factorizations. Each one of these corresponds to a different maximal Cohen-Macaulay R module, where R is this guy above. And so we see that this ring here does not have finite Cohen-Macaulay type. So how would you know that otherwise without matrix factorizations? I have no idea, but with matrix factorizations, it's a nice, quick, easy piece you can write down. Okay, so the next thing I want to get into is the branched cover situation. So first we're going to talk about double branch covers. So I will keep the same setup, except now I'm going to assume that my regular local ring is complete and the characteristic of the residue field is not 2, and that's it for the assumptions for now. So what is the double branch cover? So we keep having the hypersurface ring, which is S mod F, then a new hypersurface ring, which I'll denote as R with a sharp, where I adjoin a new variable, and then I mod out by F plus Z squared is the double branched cover. Double branched cover of R. Okay. And so the main theorem that I want to tell you about with double branch covers comes from Knörrer, also from 1987. And it says the following. So what Knörrer identified was that if you have a hypersurface ring of finite Cohen-Macaulay type, R as finite CM type, then this happens if and only if the same is true for the branch cover, so R sharp. Right. So this is Knörrer's theorem, and I'll say a little bit more about it in a second, but I do also want to point out that connection with matrix factorization that I was trying to emphasize before. So if R has finite Cohen-Macaulay type, we already mentioned that's the same thing as saying F has finite matrix factorization type, where I didn't really say those words before, but if the category of matrix factorizations has only finitely many indecomposable objects, that's what I mean by finite matrix factorization type. So these two are equivalent because of Eisenbud's theorem. That's what we had before. But then we can apply Eisenbud's theorem again on the right-hand side because R sharp is also a hypersurface. So the same idea works, just with a different equation. So F plus Z squared having finite matrix factorization type, meaning the category of matrix factorizations of F plus Z squared has only finitely many decomposable objects. That's equivalent to R sharp having finite CM type as well. And this is also Eisenbud's theorem. And then we can connect the dots, and these two become equivalent as well because you can go around the circle. So I've learned to think of all these statements meaning the same sort of thing, whereas Knörrer's original statement is just about the hypersurface rings, but it's all really the same. Okay, so one maybe small corollary that I'll try to sneak in here that doesn't like when I write in the corner, so I'll put it here. So the corollary, if this means anything to you, what one result from that comes from Knörrer's theorem is that simple, or in other words, ADE singularities of any dimension have finite Cohen-Macaulay type. Have finite Cohen-Macaulay type. Okay, and this is a big deal because the search for rings with finite Cohen-Macaulay type in any dimension bigger than 2 is really difficult. There are very few examples at all, except for if you have a hypersurface. They are completely understood, and it's really in part due to this theorem by Knörrer. Okay. So Knörrer's theorem says that R and R sharp have finite Cohen-Macaulay type at the same time. And let's talk a little bit about how that goes. So one key ingredient that Knörrer uses is actually a non-commutative ring. So you have to take a little bit of a detour out of commutative algebra and talk about a non-commutative ring. So same setup as before, complete regular ring with the characteristic of the residue field equal to 2. So my R is still my hypersurface ring. I have the branched cover, the double branched cover as before. And then what you might notice when you have the double branched cover, it comes along with an automorphism. Which does the following. So it fixes S pointwise. and then it sends z to minus z. And if you think about it a little bit, this thing has order 2. So if you close it with itself twice, you'll get back to the identity. And what you can do from this, so this is a group, this forms a group of order 2 acting on the ring R sharp, and you can form what's called the skew group algebra. Form the skew group algebra, which I'll denote as R sharp bracket sigma, like that. So what is this skew group algebra? Well, it's really closely related to the group algebra, but the multiplication is given a little bit different. So it's formal sums of the form A plus B sigma for A and B in the hypersurface. And then the multiplication is given by the following rule. If you do A times A sigma I, you want to multiply that by B. Let me move this down a little bit. So if you have A sigma I, you want to multiply that by B sigma J. In the group algebra, you can just commute the ring elements past the group elements, but with the skew group algebra, in order to move the B past the sigma I, you have to pay the price of evaluating the automorphism at B. And then this becomes I plus J, like so. And I've written it with I's and J's. There's only two, there's sigma and sigma squared, or sorry, it's sigma and the identity here, but I'm going to use this again later. So we'll just keep it like this for now. And that's for A and B and R sharp. So that's just the formation of this non-commutative ring. So what does this have to do with matrix factorizations? Well, what Knörrer proves is that the category of matrix factorizations is equivalent to the category of MCM modules over this R sharp sigma. Let me see if I meant to write this on the next page. Of course I did. So let's write it here. So the category, what Knörrer shows is the category of matrix factorizations is equivalent to the category of MCM modules over this non-commutative ring, the skew group algebra. But what does MCM mean over this non-commutative ring? So all I mean by this subcategory here is R sharp sigma modules, which are actual maximal Macaulay over R sharp. So R sharp lives inside of R sharp sigma by sending R to R times the identity, just like in the group algebra situation. And so you consider any R sharp sigma module as an R sharp module. The ones that are MCM over R sharp will live in this subcategory. Equivalently, this actually turns out to be the R sharp sigma modules, which are free over S, the base ring that we started with all the way back at the beginning. Okay, great. So this is, when I first learned about this theorem, is sort of surprising, because why should matrix factorizations of F, which really are connected with MCM R modules, why should the double branch cover, this F plus Z squared, why should it be involved right from the beginning? Knörrer sort of identified that F plus Z squared was important and needed to be realized, but it sort of was lurking the whole time. And that was sort of shocking to me. So with that in mind, the motivating question for the rest of the talk is going to be, what if we consider higher powers of Z? So F plus Z to the D for D bigger than 2. That'll be sort of my theme for the rest. Okay. Excellent. So maybe one thing else I should say, how does this theorem I just wrote down help with the main theorem of Knörrer's that I was mentioning about how R and R sharp have finite Macaulay type simultaneously? Well, maybe I can change colors for a second. So this guy we know is connected to MCM R by Eisenbud's theorem. And then it turns out if this category has finite type, then that's going to happen if and only if this category does as well. So R sharp will have finite Macaulay type if and only if this non-commutative ring has the same type of property with respect to this subcategory of modules. Okay, so that's how you make the leap, is you have this intermediate step where you convert from matrix factorizations to modules over this non-continuous. Okay, let me go back to black and then we'll switch. See, there's my problem. Ah, we did it. Okay, so now I want to talk about the new stuff, which is going to be to talk about the d-fold branch cover, which is that f plus z to the d that I was referring to. First, we have to detour through d-fold matrix factorizations. So let's talk about this. So now I'm going to fix an integer bigger than or equal to 2. I'm going to call it d. I'm going to take the same assumptions on my, I don't need these at first, but I'm going to need them in a little bit. So I'm still going to take a complete regular local ring. And I'm going to, the only thing different is I'm going to assume the characteristic does not divide d of k, the characteristic. And I should have been saying before that a lot of this needs algebraically closed as well. And I may not have mentioned that, but we'll just throw it in now. Okay, so matrix factorization now, this definition is going to look very similar. Of f, but now with d factors, is essentially the same definition as before, except we're going to allow for more matrices. So it's a tuple phi1, phi2, up to phi d, such that their product is f times an identity matrix. So the phi are square with entries in S still, and their product in this order, you have to sort of choose an order, give you f times an identity matrix. So it's a tuple. Entries in S such that you have this equation. Okay, so first of all, it's very similar to the other definition. We just have more matrices. The second thing you might ask is what happened to the other product that we had from before? Well, you might take a second to think about it, but what happens is that because these matrices are all square of the same size and their product is this non-zero divisor f, you get for free that all the cyclic permutations of these matrices starting in this order also are f times an identity matrix. So you get d cyclically permuted matrix factorizations from this first one, and those are going to come back up again later. Okay, and this is for all I. For simplicity, I'm going to also write mf of f for the category of matrix factorizations with d factors, but I'll give it a little d as a superscript to indicate that I mean with d factors. This is the category. Also say of d-fold matrix factorizations of f. Okay, great. So let's start with very simple example. So we're just going to take an arbitrary element f in our ring, our regular ring, and let's focus in on the case d equals 3 for a second. So the first thing we can do is we can just write down these really silly factorizations, which look like the following. So we have f, 1, 1, 1f, 1, and 1, 1f. And so what I mean here is these are 1 by 1 matrices, meaning elements of the ring. And if you take the product of all three of them, you get f. That's the idea. So these are 1 by 1 matrix factorizations of f. Okay, these are particularly silly, but they are actually important. And so as a quick little side note, I just want to mention, probably not going to say much more about this, but these are actually precisely the indecomposable projective objects in this category of matrix factorizations. These are precisely the indecomposable projective matrix factorizations of f. And even more, they actually turn out to be injective as well. And they are injective. Furthermore, and I won't write this down, but if you are handed a matrix factorization, you can build a morphism which maps onto your matrix factorization from a direct sum of copies of these three above. And similarly, you can embed a matrix factorization into a direct sum of these. So in other words, this category has enough injectives, it has enough projectives, and the class of injectives and projectives coincide. So what you get actually is that this category is Frobenius. So if that means anything to you and you're interested, what the follow-up to that follow-up is that, that means that if you look at the proper stable category, it's going to be canonically triangulated in this situation. And all of this does not require that S is complete or anything like that, but I guess I assumed it in the beginning. But thank you, Alapan. No, there's nothing particular about d equals 3. It's just easier to write down and really concretely see the tuples. So nothing special about d equals 3. It's true for all d greater than or equal to 2. So this is known for d equals 2 either by thinking about the category, the category of MCMR modules has this fact, but it's also true for all d greater than 2. Thank you. Excellent. Okay, so those are silly examples to write down, but they turn out to be kind of important. Let's do at least a little bit more interesting of an example before we go on. So I wrote this one in advance because they're bigger matrices, but it's back to our polynomial we had before, x cubed plus y to the fourth in these power series ring in two variables. I'm going to assume that I have a primitive third root of unity in my field, and this is related to the completeness and the field being algebraically closed. So it is useful to have these kind of roots of unity laying around. I just noticed a typo, I'm missing the square there. But anyway, so we can write down a 3 by 3. So this is a 3 by 3 matrix factorization of x cubed plus y to the fourth with 3 factors. Like so if you multiply these out on your spare time, when you have some spare time, you're just utilizing the fact that the sum of these cube roots of unity equals 0, and everything just cancels out beautifully, and it works. And this sort of construction is not special to this polynomial at all. That you can cook up all sorts of ones that look exactly like this, basically. So those are pretty nice. Okay. I think that's all I wanted to say about this one, mostly just so you can see that there are other interesting examples. Oh, the other thing I wanted to mention is that it's worth noting that this is a reduced matrix factorization too. So note that it's reduced, meaning all the entries live in the maximal ideal of our power series ring. Okay, so now I think I can tell you about the first main result. I think there we go, zoomed in on accident. So the first main result is just a direct extension of Knörrer's theorem before, but now in the arbitrary D case. So we have S is the same assumptions on S from before. So it's complete, regular local ring. The characteristic does not divide D, and our field is algebraically closed. We are also going to want a primitive d root of unity in our field. So let's let omega and S be a primitive d root of 1. We still have our hypersurface ring is the same as before, but now I'm going to introduce the d-fold branch cover, which is still going to be denoted R sharp, but it's going to be, we adjoin a new variable, and instead of modding out by f plus z squared, we now mod out by f plus z to the d, like so. Okay, so this will be the d-fold branched cover. Well, if you form this ring, the first thing you notice is that there exists an automorphism, just like before, which fixes S pointwise and sends now it sends z instead of to minus z, it's going to send it to omega times z. You get a automorphism of R sharp of order D. So now you have a group of order D, a cyclic group of order D acting on this hypersurface ring R sharp. You go ahead and you form the Skew group algebra extremely similarly as before. I mean, it's the same construction. It's just a little more complicated now because you have a group of order D. And then the actual result is that the category of matrix factorizations of F with B factors is equivalent to this same type of subcategory of modules over the Skew group algebra. And just to be super clear, I'll just write it again. This is R sharp sigma modules, which are MCM over R sharp. Okay, so it looks almost exactly the same. The only thing different from what I wrote is this D right here. But remember, this R sharp is now the D fold branch cover, and sigma is an automorphism of order D. So things have changed slightly, but it all lists exactly how you would want it to. Cool. Okay, so I'm going to tell you a little bit about how this proof goes, but first I just want to mention some interesting properties of this ring. So again, it's a non-commutative ring. I'm going to call it gamma for the time being. If you go look at gamma as a module over itself on either side, it has finite injective dimension. So if you look at the injective dimension of gamma as a module over itself on the left or on the right, these are both finite and they both equal the dimension of S, the regular ring you started with. So this is a non-commutative ring, but this is, I'm thinking of this as like it's Gorenstein-like property. And these things have names. If you have a non-commutative ring that has precisely this property, it might be called strongly Gorenstein or Iwanaga Gorenstein, something like this. So people study these sort of things. The second thing I want to say is that if you have any finitely generated module, gamma module, all my modules are on the left for this non-commutative ring, but I failed to mention that. So any finitely generated gamma module M has a projective resolution, which is eventually periodic with period at most 2. So if you are familiar with matrix factorizations, then this Eisenbud theorem gives a very similar statement to modules over a hypersurface ring. If you have a commutative hypersurface ring, any finally generated module, if you go far enough back in the minimal free resolution, it's eventually periodic and given by the periodic parts given by matrix factorization. So this is giving a very similar type statement, except this is a non-commutative ring. So for me, this is, I'm thinking here that R sharp sigma is kind of behaving because of these two properties, at least homologically, like a non-commutative hypersurface. So this is just a side note, but hypersurface. Okay. Excellent. Yeah, and it doesn't matter what D is, you still get periodicity of period at most 2. So even if D is large, the periodic thing that's happening is still period 2, which I also found interesting.
And
Okay.
sorry, if I may ask, and
No,
do the eventual maps have anything to do with the matrices in your matrix factorization or no? They do.
They do, yeah. Okay. Yeah, that's a good point. I should be a little careful because I'm thinking about it on the side of matrix factorizations. But I'm fairly certain that they should be very closely related. You build it directly from the matrix factorization. So yeah. Excellent. Okay. So yeah, just a little bit about the idea behind the equivalence. And I skipped this before when I was talking about Knörrer's theorem in the D equals 2 case, because this is really the same. It's the equivalence is constructed basically the exact same way. So let's just talk about it. So if you have an MCM R sharp sigma module, like we said before, that means it's also an MCM R sharp module, which means that n is free over S, as we said before. Okay, so then let's consider the map phi, which is multiplication of, I can't spell, by Z on N. Okay, so R sharp is, again, F plus Z to the D. So we can look at multiplication by Z on N. And what we get from this, so we pick an S basis for N and consider N as consider phi as a matrix, square matrix with entries in S, meaning no Z entries here, because we've written it as with an S basis. Then what you get is, if you take the product of phi with itself D times, well, this is multiplication by Z to the D. But we're on this hypersurface ring F plus Z to the D is 0. So this is actually multiplication by minus F. So this is negative F times an identity matrix. Okay, and so you have this pesky minus sign laying around, but you can deal with that one way or another. And so the point is that from N, you're getting a matrix factorization. You're getting a D-fold matrix factorization of F, approximately of the form phi, 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 D times, just concatenated with itself, D times. And like I said, you do need to do something about this minus sign, but once you do, this is essentially how the functor goes. By the way, the size of this matrix factorization is whatever the rank of N is over S as a free S form. So the size of these matrices is just the rank of S. Okay, so from this MCM R sharp sigma module, we're associating to it a matrix factorization. This is not exactly how the functor goes. I'm sweeping under the rug a little bit the role of sigma. In particular, you might notice that what I've laid out here would apply to any MCM R sharp module. Sigma is sort of, I'm not telling you how sigma is working at all. So I want to run with that a little bit. So how am I doing on time? Okay, good. So notice this construction I just did applies to any MCM R sharp module. Okay, and so what I mean is, if you do include sigma, you get a genuine equivalence of categories. But if you just do this other construction starting from an R sharp module, you don't get an equivalence of categories, but you do get some other interesting stuff. So I'm calling the functor which is going, the two functors which go in between category of matrix factorizations with D factors and these MCM R sharp modules, flatting and sharping. So sharp and flat do not form an equivalence. But what they do is the following. So let's let N just be a good old-fashioned MCM module over this commutative hypersurface ring R sharp, and we're going to let X be a matrix factorization of F with D factors. And if you consider the each of these functors in either order, so if you take N, you flat it to make it into a matrix factorization, and then you sharp it to send it back, what you get is a big direct sum. So you don't get back N because this does not form an equivalence, but you do get back N as a summand. So you get a direct sum of some things that look like this. So each of these is just restriction of scalars by the automorphism sigma raised to the I power. So you get a direct sum of all of those. And then on the other hand, if you do X sharped and then flatted, so you make it into an MCMR sharp module and then send it back, you don't get back X exactly because it's not an equivalence, but you do get back X as a summand in the following way. So you get a direct sum of what I call T to the IX, and what these T to the IX are just those cyclically permuted matrix factorizations that I was talking about before. So this is phi plus 1 up to phi d, and then up to phi minus 1, like so. Okay, and that's if X started as the phi 1 up to phi d. Excuse me for that. Okay, so running slightly low on time, so let me just tell you the punchline. What this leads to is that the representation type of MCMR sharp modules and the category matrix factorizations with D factors, there's not an equivalence there, but the representation theory is still connected. So let me write that down. So just for simplicity, I've been alluding to it before, but I will say that F has finite D-fold matrix factorization type. If up to isomorphism, there are only finitely many indecomposable D-fold matrix factorizations. And so what Graham Leuschke and I were able to show is that, and it basically follows from this proposition on the previous slide, is that if you have F with finite D-fold matrix factorization type, this happens if and only if R sharp has finite coma color type. So the matrix factorization category, that representation theory, is still linked to the representation theory of the D-fold wrench cover. So if you think back to that box that I drew before with all the equivalent statements, some of those equivalences are no longer true, but this is one that's, at least to me, was sort of surprising that this is the one that lifted to the arbitrary D case. Okay. Right. So I only had one more thing to say, so I'll just squeeze it in at the end here. So what you might notice is that when we're talking about hypersurfaces that look like this, you added on a term z raised to the d power. So if you're familiar with simple or ADE hypersurface singularities, what you might notice is that for most d bigger than 2, so for most d bigger than 2, you usually don't get a simple ADE hypersurface from adding on a term of the form z to the d. So you can take that idea and see how far it goes and write down the following corollary, which is that if you're going to have finite D-fold matrix factorization type, you have to be of type AN, basically. So I'll just spell this out and then I'll wrap up from there. So if you have a, again, we're in a power series ring, algebraic closed field, now of characteristic 0, and I'm talking only specifically about the case d greater than 2 here. The case d equals 2 is really the classification of simple hypersurface singularity. So this is only for d bigger than 2. And F has got finite D-fold matrix factorization type if and only if F is up to a change of variables, one of the following in the list here, and D has to be one of the associated ones in the second column. So if you're A1, you can have finite D-fold matrix factorization type for any D bigger than 2. But as soon as you're A2 or higher, the D is restricted, and you can't do anything more complicated than being a sum of squares plus the last variable to some power, and the power has to be less than or equal to 5. Okay, so yeah, so I think I'll stop there. Thank you all very much for listening, and happy to answer any questions.
Well, let's thank Tim. Questions for Tim?
I noticed that the example you gave with, I can't remember if it was x cubed plus y to the fourth or flipping the powers, that when you went to 3, you got a 3 by 3 matrix. I mean, if you go to any old D, will it be like just a D by D matrix?
So if you have, as long as you want your matrix to be, your matrix factorization to be fairly non-trivial, then if you have an irreducible polynomial with lowest degree D, for example, then yeah, they need to grow as you get higher degree polynomials, if that makes sense. But if your polynomial is not irreducible, lots of weird things can happen. And the one thing that I sort of haven't talked very much about in this talk is that in the case D equals 2, we said that Eisenbud's theorem says that it's reduced matrix factorizations you care about, but in a very kind of concrete way, when you have D greater than 2, you sort of can't avoid matrices with unit entries. So you can't just look at the reduced ones. In fact, they're much more rare in the D greater than 2 case. Yeah. So does that answer your question?
Yeah, thanks.
There is a construction, I think maybe to say one more thing, there is a construction if you have a homogeneous polynomial of degree D, you can build some D, how big would they be? It would be, it depends on how many terms there are, but they're going to be 2 to the power D or something like that, or D minus 1. I can't remember exactly.
Other questions?
But I mean, I probably misunderstood. I think Eloise asked similar questions. So if I suffix a D and start with a D-fold matrix factorization, so in D equal to 2, so this Knörrer's periodicity actually gives you a maximal coherent Mcmr module over the ring R, right? The hypersurface ring R. Mm-hmm. So when D is greater than 2, do you get any similar object over R?
Yeah, so I didn't squeeze any of this in here. Main reason because I don't have it written down anywhere that people can go read. But yeah, so maybe I can, do I have any blank space? I guess I didn't add a blank slide. Yes, the connection between D-fold matrix factorizations and MCM R modules, like the precise connection, was something that I looked into for a long time. And Eric Hopkins out of Nebraska last May, his dissertation proved a really interesting thing, which is that in the case D equals 3, the category of matrix factorizations with 3 factors is equivalent to the category of short exact sequences of MCM R modules. Just on the nose, like that is it's a much bigger category than I thought it was ever going to be. That's what he showed. And then for arbitrary D, you can cook up something that's very closely related to what Eric said. And yeah, I wish I could tell you to go read something at this moment, but I haven't posted it anywhere. But yeah, there's a nice connection there.
Sorry, who was the person? Whose thesis was it?
His name is Eric Hopkins. He's a student of Mark Walker's at Nebraska. Okay. Yeah.
Okay, and yeah, another question is, so if you start with a D-fold matrix factorization, so I guess from there you can cook up a 2-fold matrix factorization, right?
Sure. Yep.
Yeah. So I don't know whether it's a map of categories and so on. And also, like conversely, if you start with a 2-fold matrix factorization, you can like throw in some identities and cook up a D-fold matrix factorization. So first of all, are this map of categories of matrix factorization? And if yes, so are these maps well understood?
The answer is yes to the first question. And are they well understood? So if you have a matrix factorization like this, or you just, this one here is a 2-fold matrix factorization, then you just pop in an identity matrix. So these are not, I'm not ruling those out. Those are perfectly viable options in the category. So what can I say about this? I'd really like a good way of avoiding these type of factorizations. It would be really nice, because really what this is like, it's like the category of 2-fold matrix factorizations sitting inside the category of 3-fold matrix factorizations, and so on, by adding identities. So I think this is a I think it's a fully faithful embedding. I mean, if that does anything for you. But
Yeah, that yes,
I
there's
would have
something.
to think. I'd have to think about it a little bit. But yeah. But
I mean, those feel like face and degeneracy maps somehow in some big combinatorial thing.
so I'm not an expert in anything in this area, but yeah, so there are some connections to K-theory, and that's precisely, I think, what they should be. They're basically face and degeneracy maps. Yeah, right.
Okay, and like if you keep gluing these objects, then if these are like face and degeneracy maps, so do you get something meaningful?
That I don't know. I would love to know.
Okay.
Yeah, I think that's basically exactly what Carrie's saying is what they should be, and then I don't know what happens when you do that.
Okay. Yeah, thank you.
Very cool. Yeah, absolutely.
Last call for questions. All right, let's thank Tim again.